We start our new unit on magnetism today for the third time by defining a new term, a magnetic domain, which is a tiny little region inside a ferromagnetic material that we represent by arrows. Now, there's a couple things in here I got to clarify. One, a ferromagnetic material. What is a ferromagnetic material, Christian?
Iron.
An example of a ferromagnetic material is iron, yes. Where does that come from? Iron, the chemical symbol for iron is Fe, and sometimes you see it ferrous or ferro, right? Ferrous oxide is an old term for iron oxide. Iron is an example of a ferromagnetic material, probably the most common example. So is steel. Steel is an alloy of iron. So is cobalt, an example of a ferromagnetic material. In general, we say a ferromagnetic material is a material that can become magnetized. Iron, steel, cobalt, every ferromagnetic material can become magnetized. Now, the other thing that I wanted to clarify here is this whole phrase down here that we represent by arrows. If we look at a ferromagnetic material under a microscope, we're not going to see a bunch of little arrows pointing in whatever direction, right? We're going to see, if we could magnify it enough, then we would see electrons spinning in certain directions. We represent these domains that have to do with spins of electrons by arrows. It's too difficult to draw the spins of electrons, so we're going to draw arrows to represent those spins of electrons. This domain is a tiny little region inside this material that can become magnetized, and we're going to represent these domains by tiny little arrows. Now, when these domains align, or in other words, when the arrows that we represent the domains with point in the same direction, then we would say this ferromagnetic material has become magnetized. In other words, we got a magnet. It's not just the piece of steel that the leg of your desk is made of. It's actually a magnet now. The domains will always point towards the north end of the magnet. That is when it's become magnetized. This is a non-magnetized ferromagnetic material. This is the leg of your desk, or it's the filing cabinet over there. It's whatever piece of steel or iron or whatever, but whatever piece that's not exhibiting a magnetic effect right now. This is a magnet. The domains don't have to be pointing in exactly the same direction, but they have to be aligned more or less in the same direction. Once they become aligned, we define the poles of that magnet. We would say this is the south pole and this is the north pole. We arbitrarily define the direction of the domains as being from south to north. So you see this bottom diagram is a magnet. The domains have become aligned. Well, how do we align these domains? How do we get them pointing in the same direction? Well, there's a couple basic ways we can do that. One, if we have a non-magnetized ferromagnetic material with domains pointing in whatever direction, random direction basically, we bring another ferromagnetic material nearby that is magnetized, that has the domains pointing in the same direction, then these green domains will affect the black domains here and cause the black ones that we have drawn here to become aligned. So these aligned domains influence these unaligned domains to become aligned, to point more or less in the same direction. Now, the other way to do it, we'll talk more about this one after Easter break, is to take a piece of steel or iron or cobalt or whatever ferromagnetic material you have and wrap a wire around it. Apply an electric current through that wire from a battery or from whatever. The electric current, you're going to learn after the break, generates a magnetic field, and that magnetic field can magnetize that ferromagnetic material that the wire's wrapped around. So one, bring another magnet nearby. Even better, rub it against it. Okay, you probably did this in elementary school when you looked at magnetism. You took a nail and you took a magnet and you rubbed the nail against the magnet. The nail became magnetized. If you bring the magnet nearby, it'll become magnetized. If you rub it against it, it'll become magnetized more efficiently. That's number one. Number two, you might have done this in elementary school as well. Taken the nail, wrapped wire around it, hooked it up to a battery, and then tried picking up thumbtacks. Okay, or paper clips, did you do that in elementary school? Yeah, you make an electromagnet. Okay? That's the other way of magnetizing a non-magnetized ferromagnetic material. And I'm going to star that one because we'll look at that one, why that happens, and so on in more detail, as we say, after the break, Monday after the break. We have three laws of magnetism that describe interactions between magnetic fields here now. First law, real similar to what we saw with the laws of electricity. Second law, same thing. Third law is a little bit different. Anybody remember the first law of electricity? Like charges repel each other. Well, we're not talking about charges now. We're talking about poles, North Pole and South Pole versus positive and negative charge. But what do you think the first law of magnetism would be? Yeah, like poles repel each other. It doesn't really matter what order you list them in, but that's the first one that we listed with electricity, so that's the first one that we'll list with magnetism. Like poles repel each other. It's the second law of electricity. Opposite charges attract, so opposite poles are going to attract, or unlike poles are going to attract each other. And finally, the third law of electricity. Sorry? Conservation? No, that's kind of like, it was like a fourth law that we put outside of this one. Yeah? Yeah, good. Charged objects attract neutral objects. And does anybody remember why that happened? Why charged objects attract neutral objects? Yeah, because of induction. We induce a temporary separation of charge. With magnetism, we would say that magnets, or both north and south poles, magnets attract non-magnetized ferromagnetic materials. Got to be ferromagnetic, right? You're not going to have a magnet attracting a piece of paper. Magnets attract non-magnetized ferromagnetic materials. Why does that happen? Well, because the magnet causes the domains in the non-magnetized material to become temporarily aligned. So it's almost the same thing as with electricity. We're inducing not a temporary separation of charge, but rather we're inducing a temporary alignment of domains in the non-magnetized material. So if this is our non-magnetized material with domains pointing in random directions, and we bring something nearby it that is magnetized with a south pole and a north pole, that magnet will be attracted to the non-magnetized material because these domains right here inside this non-magnetized material become temporarily aligned in the direction of the domains in the magnet. So this thing that was just a second ago not magnetized now develops a polarity associated with it, a north pole and a south pole, and you notice the side that's closest to the thing that's doing the magnetizing is opposite, so it's going to attract each other. Right? Just like we induce that temporary separation of charge, and the side closest becomes oppositely charged, well, we induce a temporary alignment of domains, and the side that's closest becomes opposite pole, which means it's going to attract each other. You take this thing away, this one that's doing the magnetizing, what do you think is going to happen to these domains? They're going to more or less go back to random, and it might not happen instantly. You might maintain some sort of magnetic effect right here in this thing that was non-magnetized, but it's not going to be for that long. That is, unless this thing has been nearby for a long period of time. We actually notice this in buildings, high-rise buildings that are made out of, well, what's the primary structure of high-rise buildings? Steel, right? Which is a ferromagnetic material. Okay, if that building is made, let's say that building was made 30 years ago, 40 years ago. Okay, it's been sitting in the same place in the Earth's magnetic field. The Earth's magnetic field, which by the way is a fairly weak magnetic field, but sitting in the same place in the Earth's magnetic field for 30, 40, 50 years. Okay, what happens over time? The Earth's magnetic field actually causes the domains in that building to become aligned. And because it stays there, then the effect of that is much more permanent. So we would know, it's not a strong effect, but it's a measurable effect in that steel-framed building becomes magnetized because of, over time, the Earth's magnetic field. Now, sometimes, like sometimes you're finishing your, your basement or something, you're building walls, putting metal studs up. Those metal studs are made out of, well, a lot of times you use wood, right? Spruce, but sometimes you use metal. Those metal studs are made out of aluminum. You wouldn't notice the magnetic effect there. Okay, it doesn't matter how long those aluminum studs are there for in your wall, you're not going to notice a magnetic effect. How come? It's not ferromagnetic. Aluminum's not ferromagnetic. Even though it's a good conductor of electricity, it's not ferromagnetic. Just like you wouldn't notice a magnetic effect in your wood walls, you're not going to notice it in your aluminum framed walls either. Happens in bigger buildings because it's steel, which is ferromagnetic. Let's talk a little bit about magnetic fields now. You guys remember that we defined an electric field as this was question number 1 on your unit test, I think, a region in which an electric force could be experienced by an electric charge. How do you think we're going to define a magnetic field? A region in which a magnetic force could be experienced either by a magnet or a ferromagnetic material. It's like we define a gravitational field as a region in which a gravitational force could be experienced by an object with mass. So if I put a magnet in a certain area and it's affected, or just a ferromagnetic material in a certain area and it's affected, then there must be a magnetic field present. Of course, magnetic fields surround magnets, and electric currents or moving charges, and we said we'd talk about that the day after we get back from Easter break. And of course, just like electric fields and gravitational fields, because they have an influence in a particular direction, we're going to say that they're vector fields. All right, I want everybody to take a look at the first page of the handout that I gave you at the beginning of class. You see 3 diagrams on that page. The first diagram looks like this. We have a magnet with a north pole and a south pole and a bunch of little stars around it. We're going to do a little activity here, not for marks, not for handing in, just a little activity at your desks with a partner or a couple partners, where you're going to replicate the diagrams that you see on the page and draw diagrams or complete the diagrams with little arrows representing the direction that a compass will point when placed in all those different positions where the stars are. So for instance, if you put this magnet, this single magnet, as you see in diagram 1, in the middle of your desk, and you see a little star right above that magnet, then I want you to put a compass right where that star is and see which way the arrow points. I want you to do that for all the little stars and draw little short arrows indicating the direction that the compass needle is pointing. You go on to the next diagram and then go on to the third diagram. When you're finished, we'll come back and we'll connect the dots. Do a little kindergarten, grade 1 activity, connect the dots. The idea will be that we're going to plot the magnetic fields surrounding simple bar magnets, and then surrounding 2 bar magnets, and then 2 other bar magnets in a different scenario, and see what that magnetic field looks like. All right, everybody should have a diagram now that looks like this with arrows pointing in, it might seem like almost random directions, but when I start drawing those arrows on this diagram and connecting the dots, hopefully you're going to start seeing a pattern. You should see something that looks more or less like this. It's not going to be exactly the same as mine, okay, but it should be close to the same as mine. How many people have a diagram that looks more or less like this one? Good. Let's connect those dots now. If we connect those dots, we're going to find that the magnetic field surrounding this bar magnet is going to look something like this. Notice the magnetic field is pointing this way, away from the north. It's pointing toward the south. That is, if we look at the outside of the magnet, it's going away from the north toward the south. If we actually extended the magnetic field lines, completed the loops right through the magnetic field lines would actually point the other way, from south to north. But we don't usually look at inside the magnet. We almost always look at outside of the magnet, and they're going to point from north to south there. So you should see something when you connect the dots that looks pretty much like this. Now, if we take a look at my second diagram, where we have two magnets, a north against a south, then we should see field lines that look, or we should see arrows that look kind of like this. Again, not necessarily perfect, but close. These are backwards. That's backwards. There we go. And there we go. So it should look something like this now. Now, this looks even worse in terms of what appears to be randomness. If we start connecting dots or joining dots together, then we should see something like this. Once again, the field lines are pointing away from the north toward the south, like this. What do you notice about those field lines in between the north and the south of those two magnets? Yeah?
It still goes from north to south, but it goes from one magnet to the other.
Good, perfect. It still goes from north to south, but it's not going from the north of one magnet to the south of the same magnet. It's going from the north of one magnet to the south of the other magnet. In other words, the field lines join up. Right? The field lines in between join up. What do you think is going to happen when we have field lines that join up? Just like with electric fields, field lines that join up in magnetic fields cause a force of attraction. There's a good chance, in fact, there's nearly 100% chance that you're going to see a diagram of magnetic fields on your next unit test coming up in 3 weeks. If you remember the diagram, if it's exactly the same as the diagram you've seen before, that's great. Okay, that's perfect. Okay, if you don't remember the diagram, that's okay too. All you need to do is look at the diagram and remember two things. Okay, A, if the field lines join up, then we get a force of attraction. Should we get attraction here? Yeah, north against south, they attract each other, right? The field lines should be joining up. And the other thing to remember is that the field lines go away from the north and they go toward the south. Let's draw one more. The last one that you guys drew, we should get something that looks like this. Okay, all kinds of different field lines going seemingly everywhere. Like this. How many people get a diagram that looked something like this? Okay, this one actually looks a little bit better than the last one, right, in terms of how crazy it looks. If we start joining these together, it's going to look something like this. What do you notice about, well, let's draw the direction of the field lines first. Once again, from north to south, same as it has in all the other diagrams. The field lines are always going to go north to south as long as they're outside of the magnet. Inside of the magnet, if we continue the loop around, they would go from south to north, but we don't usually look at that. Usually outside. What do you notice about that little area in between the two magnets where we have north against north? These field lines do not join up, and as a result of them not joining together, we get repulsion, right? When field lines don't join, just like we did with electric fields, we get a force of repulsion. So once again, you get a diagram on a test, even if it's one you've never seen before, some scenario of magnets set up that you've never seen before, that's okay. Remember that the field lines go away from the north and toward the south, and remember that the field lines join up, we get attraction, and the field lines don't join up, we get repulsion. Magnetic fields are vector fields. They have a direction. How do we define the direction of these magnetic fields? What's one way? Okay, you've just gone over both of them in the last 10 minutes. What's one way we define the direction of the magnetic field? Think back to your activity. How did you measure the direction of the magnetic field? Yes, but let's talk about the other one first. In your activity, how did you measure the direction of the magnetic field? Remember, with an electric field, the field was the way that a positive particle would move when placed in the field. A magnetic field is the way that a compass needle points when placed in the field, the direction that a compass needle points. So we sub in a compass needle for a positive charge. We look at which way it's affected. Remember the other way we define the direction of an electric field? The way that a positive would move if placed in the field, and away from the positive toward the negative. We're going to define the direction of the magnetic field in a second way as away from the north and toward the south. It's not the same thing as an electric field, right? But you can see how analogous it is, right? We define the field as a region in which a magnetic force could be experienced. We define the direction as the direction that a compass needle would move if placed in the field. We define it as away from north toward the south. So we just replace a few words with other words, and all of a sudden we've got this whole lesson on magnetic fields versus electric fields.